A solid neutral is a continuous, uninterrupted conductor that connects the neutral busbar to the neutral terminal on the main circuit breaker in a panel board. It is typically a thick copper bar or wire that provides a low resistance path for the return current. When comparing a solid neutral to other types of neutrals in a panel board, firstly, there is a floating neutral. A floating neutral is not connected to the neutral terminal on the main circuit breaker. It is only connected to the neutral busbar and serves as a return path for unbalanced loads. Floating neutrals can cause voltage imbalances and nuisance tripping of circuit breakers. Secondly, there is a bonded neutral. A bonded neutral is connected to both the neutral terminal on the main circuit breaker and the equipment grounding terminal. It provides a common reference point for the neutral and grounding systems, reducing electromagnetic interference and ensuring proper operation of ground fault circuit interrupters. Advantages of a solid neutral include reducing voltage imbalances and nuisance tripping, ensuring a stable reference point for the neutral system, and minimizing electromagnetic interference and improving ground fault circuit interrupter performance. Solid neutrals are typically used in panel boards that feed unbalanced loads or have a high density of electronic equipment. They are also required in certain jurisdictions and for specific applications, such as healthcare facilities and industrial control systems. The key differences among solid, floating, and bonded neutrals lie in their connection points and functions. A solid neutral provides a direct, low-impedance path for neutral current. A floating neutral lacks a direct connection to the main circuit breaker neutral terminal, potentially causing voltage instability. A bonded neutral connects to both the neutral terminal and the equipment grounding system, enhancing safety and reducing electromagnetic interference. Consider a scenario in a commercial building where a panel board feeds a mix of lighting, receptacles, and electronic equipment. If the neutral connection is not solid, unbalanced loads could cause voltage fluctuations affecting sensitive electronic devices. A solid neutral ensures a stable voltage reference, preventing equipment malfunction. In contrast, a floating neutral might lead to erratic behavior of devices connected to the panel board due to the varying neutral potential. A bonded neutral, in addition to providing a stable neutral, also helps to mitigate electromagnetic interference generated by electronic devices, keeping the electrical system cleaner. The choice of neutral configuration also impacts the effectiveness of ground fault circuit interrupters. A properly bonded neutral ensures that ground faults are quickly detected and interrupted, minimizing the risk of electrical shock. A floating neutral, on the other hand, might compromise the sensitivity and reliability of ground fault circuit interrupters, potentially creating a hazardous situation. Regulations often dictate the type of neutral required based on the application and location. Healthcare facilities, for example, typically require solid neutrals to ensure the reliability of sensitive medical equipment. Industrial control systems also benefit from solid neutrals to minimize electrical noise and prevent operational disruptions. When designing or maintaining electrical systems, it is important to consult local electrical codes and standards to determine the appropriate neutral configuration for each application. Factors such as load balancing, equipment sensitivity, and safety requirements should all be taken into account. Regular inspection and testing of neutral connections are essential to ensure the continued integrity and performance of the electrical system. Loose or corroded connections can compromise the effectiveness of the neutral conductor, leading to voltage problems and safety hazards. Proper torquing of connections and periodic infrared scanning can help to identify and address potential issues before they become serious. In summary, the solid neutral plays a critical role in ensuring the stability, reliability, and safety of electrical systems. By understanding the differences between solid, floating, and bonded neutrals, and by adhering to relevant codes and standards, electrical professionals can design and maintain systems that deliver optimal performance and protect people and equipment. For instance, in a data center with numerous servers and networking equipment, a solid neutral is crucial. These devices draw power unevenly, creating unbalanced loads. A solid neutral provides a consistent low-impedance return path, preventing voltage fluctuations that could damage sensitive electronics or cause data loss. Furthermore, The high density of electronic equipment in a data center generates significant electromagnetic interference. A bonded neutral, used in conjunction with a solid neutral, helps to minimize this interference, ensuring the integrity of data transmissions and the reliable operation of equipment. In a hospital setting, the reliability of electrical power is paramount. Life support systems, diagnostic equipment, and monitoring devices all depend on a stable and consistent power supply. A solid neutral, often mandated by code, provides a reliable reference point for the electrical system, minimizing voltage variations that could compromise the performance of critical equipment. Additionally, the stringent safety requirements of healthcare facilities necessitate the use of bonded neutrals to ensure the proper operation of ground fault circuit interrupters, protecting patients and staff from electrical shock hazards. In industrial environments, where heavy machinery and variable frequency drives are common, the electrical system is subjected to significant stress. Unbalanced loads, harmonic currents, and voltage transients can all contribute to voltage instability and equipment malfunction. A solid neutral, combined with appropriate grounding and surge protection measures, helps to mitigate these effects, ensuring the reliable operation of industrial equipment and minimizing downtime. Consider a large office building with multiple floors, each housing various types of equipment, including computers, printers, and lighting systems. A solid neutral provides a stable voltage reference throughout the building, preventing voltage sags or swells that could disrupt operations or damage equipment. Additionally, a bonded neutral helps to minimize electromagnetic interference generated by the electronic devices, creating a cleaner and more comfortable working environment. When troubleshooting electrical problems in a panel board, the neutral conductor is often a key point of investigation. Voltage measurements between the neutral and ground can reveal potential issues, such as a floating neutral or loose connection. High neutral to ground voltage can indicate unbalanced loads or grounding problems, while a completely open neutral can result in severe voltage imbalances and equipment damage. Proper testing and inspection procedures are essential for identifying and resolving neutral-related issues, ensuring the safety and reliability of the electrical system. The National Electrical Code, or NEC, provides detailed requirements for neutral conductors and grounding systems. Compliance with the NEC is essential for ensuring the safety and performance of electrical installations. Articles 250.24 and 250.28 address grounding and bonding requirements, including the proper sizing and installation of neutral conductors. These requirements vary depending on the type of system, the size of the load, and the application. It is important for electrical professionals to stay up to date on the latest NEC requirements to ensure compliance and avoid potential hazards. In addition to the NEC, other standards and regulations may apply to neutral conductors and grounding systems. IEEE Standard 142, also known as the Green Book, provides guidance on grounding and bonding practices for industrial and commercial power systems. This standard offers recommendations for minimizing electrical noise, preventing equipment damage, and ensuring the safety of personnel. State and local electrical codes may also have specific requirements for neutral conductors and grounding systems, depending on the jurisdiction. Understanding and complying with all applicable codes and standards is essential for ensuring the safety and reliability of electrical installations. The selection of the appropriate neutral conductor size is critical for ensuring the proper operation of the electrical system. The neutral conductor must be sized to carry the maximum unbalanced load. The NEC provides guidelines for calculating the unbalanced load and determining the appropriate conductor size. Factors such as the type of load, the length of the run, and the ambient temperature must be taken into account. Undersized neutral conductors can overheat, leading to voltage drops and potential fire hazards. Oversized neutral conductors can increase costs and complicate installation. Proper conductor sizing is essential for ensuring the safe and reliable operation of the electrical system. The materials used for neutral conductors also play a significant role in their performance. Copper is the most common material for neutral conductors due to its high conductivity and corrosion resistance. Aluminum is sometimes used for larger conductors to reduce costs. However, aluminum conductors require special connectors and installation techniques to prevent corrosion and ensure a reliable connection. The choice of conductor material should be based on the specific application, the environmental conditions, and the cost considerations. Regardless of the material used, all neutral conductors must be properly insulated and protected from physical damage. Proper installation techniques are essential for ensuring the long-term performance of neutral conductors. All connections must be made using approved connectors and torqued to the manufacturer's specifications. Loose or corroded connections can create resistance, leading to voltage drops and potential fire hazards. Conductors must be properly supported and protected from physical damage. Conduit or other protective measures may be required in certain environments. Regular inspection and maintenance are essential for identifying and addressing potential issues before they become serious. In summary, a solid neutral provides a stable and reliable reference point for the electrical system, minimizing voltage imbalances, reducing electromagnetic interference, and improving the performance of ground fault circuit interrupters. Understanding the differences between solid, floating, and bonded neutrals, and adhering to relevant codes and standards is essential for ensuring the safety and reliability of electrical installations. The choice of neutral configuration should be based on the specific application, the load characteristics, and the environmental conditions. Proper installation, maintenance, and testing are essential for ensuring the long-term performance of neutral conductors in grounding systems. By following these guidelines, electrical professionals can design and maintain systems that deliver optimal performance and protect people and equipment.